In this video, we're going to look at finding the volume of a cone by using slicing. So we'll give this cone a height of 10 and a radius of 5. And we'll talk about how you can generalize to derive the formula for the volume of a cone. But first thing we got to do is we got to choose our ith slice. I'm going to go ahead and choose them parallel to the base because I think that's going to be easier. If I went perpendicular to the base, I can see it's going to be different over here than it is over here, and might make a little bit more work. So my slice is going to look like this. So this is my ith slice. Now the goal is to pick a slice so that you get something that's not changing anymore. That's part of what's causing the problem. So I'm going to choose it so small so that I can assume that the sides are straight up and down. Alright, so what we're going to do is we're going to want to find the volume of the ith slice, and then we're going to add up all the slices. Well, just like before, these slices are going to, like I said, these slices are going to go this direction, so we would be making slices like this. And so they're all going to have the same height. So I might call this here delta H, because they're all going to have delta H, a little change in height. That infinitely small delta H that we're eventually going to let go to 0. Also, we need another dimension. Now, notice, depending on where I pick my slice, the radius is going to be different. So I'm going to call that r sub I. Needs to have a variable if it's going to vary. So I can actually come up with the volume of this slice, but we need to think about what it looks like. If I were to take this slice and pull it out, well, it's going to be circular with a little bit of thickness. So it's going to look like a very, very flat cylinder. And so it's going to be the area of a circle, pi r squared, by r sub I squared, times delta H. That's the height. Okay? So basically, we're going to be adding up a whole bunch of these little cylinders, and that's going to be what approximates the volume of the cone. Now, one thing we should notice right away, R and H, our variables don't match, so we need to make that happen. Well, what I'm going to do is I'm going to draw a little bit cleaner drawing. If we look at this triangle directly from the side, I know from here to here is 5, and I know it's got a height of 10. Here's my r sub I for my ith slice, and I could put in h sub I for the height at that ith slice. And if I draw a let line all the way down, notice I have here similar triangles. Okay, that comes up a lot when we're dealing with slices. So I know that h sub I is to r sub I as 10 is to 5. So, what do we have here? 10 over 5 is just 2. And I can multiply that r sub I over. So I have h sub I equals 2r sub I. Well, I have r sub I. I want h sub I. So I need to solve this for r sub I. So I'm going to divide both sides by 2. And I'm going to take this and plug it into my volume of my ith slice to get pi times h sub I over 2 squared delta H, which is going to be, this is going to become h sub I squared over 4, so I'm going to write the pi over 4 up front, h sub I squared delta H. Now, to approximate the volume, we would set up a Riemann sum that would, from 0 to n, add up all the v sub i's. Well, to make that exact, we're going to let n go to infinity. We're going to have an infinite number of slices, which forces delta H to go to 0. So v is going to be the definite integral of our v sub I, so pi over 4. And I'm going to use h instead of h sub I because I've gone from the discrete to the continuous case. And dh instead of delta h because now it's an infinitely small height of that slice. Last thing I need are my limits. H is my variable. H can be as small as 0 and as large as 10. And there we have our integral set up. I'm going to pull out the pi over 4. The antiderivative of h is h cubed over 3. And we're going from 0 to 10. So, plugging in 10, we get pi over 4 times 10 cubed over 3. And it's going to be minus 0 because when h is 0, that's 0. And we're going to get 10 cubed, which is 1,000, but it's going to be divided by 4. So 250 over 3 pi. Well, let's check this with our what we know is the formula for volume of a cone, which is pi over 3 r squared h. So we have pi over 3 times radius of 5 squared times a height of 10. 5 squared is 25 times 10 is 250, so there's our 250 over 3 pi. So we did this for the specific case, but we could have done it for a cone of radius r and height h to derive this formula. So maybe give that a try.